Yes, sir.
Am I audible to all of you?
Yes, sir.
इसमें कोई प्रॉब्लम है किसी को? ये जो टॉपिक है जो मैंने लास्ट टाइम कवर किया था, if anybody is having any problem, जी successive approximation type DVM, then I'm ready to explain it today. Then I'll proceed to the new topic. So I feel that it is fine to all of you. Should I proceed? कुछ तो बोलो तुम लोग.
Yes, sir.
Anyway, now the today's topic is Q factor meter. So can anybody tell me what is Q factor, quality factor? Obviously your Q factor meter will measure the quality factor. So we had already, means even this year also we discussed the Q factor with reference to certain in certain topic we discussed what is Q factor, how can we measure it. So can anybody tell what is Q factor? What is Q factor? Yes, please. Anyone? Q factor जानते हैं भाई आप लोग? अभी सुनाई पड़ रहा है आपको? How will you define a Q factor of a coil? If you are having a coil, then how can you define a Q factor of a coil? जी हाँ भाई, आपको लोगों को सुनाई पड़ रहा है? It's a very pathetic condition. You people are not. We have discussed when we were talking about we were discussing the bridges. Then during bridge discussion on bridge AC bridges, there was certain bridge was suitable for the medium Q coil, and then certain bridge was good for high Q coil, and certain bridge was good for a low Q coil. So what is the quality factor of a coil? How will you define it? हाँ बोलो. वालेकुम सलाम. हाँ यार, मैं जरा क्लास ले रहा हूँ. क्लास के बाद I'll talk. जी भाई. हमारी राजीव कुमार.
Yes, sir.
What is Q factor? How will you define Q factor of a coil? Sabiha Khatun.
Yes, sir.
How will you define Q factor of a coil? Anybody else who knows? As per my expectation, everybody should know because we had discussed in this semester only. Means whole class of the sixth semester, you people are not aware of Q factor of a coil. Around 9 people are here. अबे फराज कामरान, आप बता सकते हैं? फराज कामरान, भाई फराज आप हैं कि नहीं है? मोहम्मद अरशद,
Yes, sir.
how can you define a quality factor of a coil?
Sir, Q factor, sir.
हाँ,
Sir,
Q factor
dimensionless unit होता है sir, losses coil का.
हैं?
Sir, dimensionless unit for the losses of a coil,
नहीं
sir.
नहीं, this is not like that. I explained it earlier also, but you people don't concentrate. I don't know. This is because of the online classes or something like that, because you people are not concentrating at all. If we are designing a coil, obviously inductor coil we are designing, but that coil will have, it is made up of wire, so that wire will have resistance also. But when we are designing a inductor coil, then obviously we desire that it should be purely inductive coil. There should not be any resistance. But that is not possible, because whatever wire that you will use will have certain value of resistance, obviously. Then our emphasis is will be that we should design a coil in such a way that it should have more dominating value of inductance than the resistance. So how can we measure quantitatively? How can we measure that whatever inductor coil that we have designed, it is having good value of inductance in comparison to the resistance? So this quality factor is basically that parameter through which we try to decide and we try to determine that how good is your coil, inductor coil. So obviously it is pretty obvious that if we want to know that, then this ratio will be called quality factor. Inductive inductive reactance, ratio of inductive reactance to resistance. So at a given frequency, if your inductance is, means your inductor is good, so obviously your numerator value will be higher and your resistance value will be, denominator value will be lower, and then you will have the higher value of the Q factor, and we'll say that this inductor coil is having more inductance at a given frequency, obviously. And then depending upon the quality of the inductor coil, we may have higher value, we may have lower value, we may have medium value. So this is the parameter which basically quantitatively tells how good is your inductor coil. Is it fine to all of you? अभी समझ में आया?
Yes, sir.
ठीक है, ये बात समझ में आ गई. अब क्यू फैक्टर मेजर कैसे कर सकते हैं? कोई मेथड आप बता सकते हैं जिससे क्यू फैक्टर, कोई भी कॉइल आपके पास आया and you want to measure the quality factor, how can you measure the quality factor of a coil? Can you recall any method that you have studied till now?
Sir, Q meter.
क्यू मीटर पढ़ा है आपने इससे पहले?
No, sir.
भाई हम तो वो पूछ रहे हैं जो आपने पढ़ा हो. क्यू मीटर तो आप यहाँ लिखा हुआ तो आपने बता दिया. आई एम जस्ट आस्किंग, कोई ऐसी चीज पढ़ी हो आपने जिसके थ्रू क्यू ऑफ अ कॉइल कैन बी मेजर्ड. एसी ब्रिजेस में हमने ये पढ़ा था. I don't know what you study. You have given sessional test also. So you have gone through all those topics also. So in um, AC bridges, the bridges which are used for measurement of inductance, those bridges can be used for direct measurement of quality factor of a coil. So bridges can be used, but bridge is a, although it's a standard method to measure anything, whatever you are measuring, whether it can be used for measurement of many parameter. So it's a standard method, but it is not direct reading type. So many time you will find that in all the cases we want that our measurement application we always prefer the direct reading type meter. Means bridge, you have to perform the experiment and then you have to calculate the value. But if you are having a meter which can directly tell you the quality factor, you just connect it and you will get the answer, then obviously it will be the better choice. So that's why Q factor is used. Q factor meter is a meter which can be used for the direct measurement of your coil quality factor. So bridge circuit can also be used for measurement of quality factor of a coil, but Q factor meter is basically a dedicated direct reading instrument for the Q factor of the coil. Now here, the what is the basis of the Q factor? You try to concentrate here. This is very simple, very interesting. Your Q factor meter basically works on the principle of series resonance. Now suppose this is a coil. This is a coil whose quality factor you are interested in finding out. This is the coil which is having a certain value of inductive reactance and certain value of resistance, and then we connect a resonating coil, a resonating capacitor in series with it. Now when means by either by varying the excitation frequency or by varying the capacitance value for the given coil, we may achieve the resonance. You must have studied the resonance in your circuit theory, you know? So I'm presuming that you are already aware of the resonance conditions and resonance circuit. So in this case, you know, by varying the capacitance or by varying the frequency for the given capacitance and the coil, we can achieve the resonance. At the resonance, your inductive reactance will be equal to the capacitive reactance. बात समझ में आई? फ्रीक्वेंसी हम ऐसी फ्रीक्वेंसी अचीव कर लेते हैं या गिवन फ्रीक्वेंसी पे ये कैपेसिटेंस वैल्यू ऐसा लेते हैं कि हमारा इंडक्टिव रिएक्टेंस कैपेसिटिव रिएक्टेंस के बराबर हो जाता है. When this will happen, though obviously inductive reactance is positive and capacitive reactance is negative, 1 upon j omega c or minus j upon omega c, and ये होता है j omega l. So these two will get cancelled. So effectively, when resonance is achieved, then in a series resonance circuit, your inductive reactance will be cancelled by the capacitive reactance. Then your circuit will be purely resistive circuit. It will behave like a purely resistive circuit. So this is what is the resonance, and so this is the condition. XL will be XC at the resonance frequency. Then obviously whatever voltage that will appear across the capacitance, means the voltage across the capacitance will be equal to voltage across the inductance, because it is a series circuit. So the same amount of current will flow in both the reactances, your inductive reactance and your capacitive reactance. So both will be equal and obviously they will cancel each other. So whatever voltage you are applying, the complete total voltage will appear across the resistance. So that's why I had written here E is equal to I into R. Now quality factor, you know, it is equal to XL upon R. That is what is the definition of the quality factor. Or since in a resonance circuit, when we are talking about this circuit, when resonance is achieved, then we can replace XL by XC, and it will be XC upon. Now we will multiply the current IXC upon IR, same amount of whatever amount of current we will multiply in the numerator, same amount of current we are multiplying in the denominator. So your expression remains same, the ratio will remain same. So Ix is the voltage across the capacitance, and E is the total voltage. IR is because whatever voltage you are applying, once the resonance is achieved, then the whole voltage will appear across the resistance, because your inductive reactance and capacitive reactance will cancel each other. So this way your quality factor is equal to the ratio of the voltage across the capacitance divided by the total excitation voltage. Is it clear to all of you? जी, ये आप सभी लोगों को क्लियर है? नहीं, हाँ नहीं तो बोलो. बताइए भाई, ये जो मैंने एक्सप्लेन किया है ये आपकी समझ में आ गया? जी, विवेक चौहान. कहाँ भाई विवेक चौहान? आर यू हियर? दे आर नॉट अराउंड. हाँ भाई मोनिश. अमन, अमन. Anyway, I don't have any problem. I'll keep on explaining the things without your response. It is up to you. Anyway, so the quality factor. So how can we find the quality factor by this particular on the basis of the series resonance circuit? So if we use, you can see that the quality factor is proportional to the voltage across the, because we can write it like this, EC, that is the voltage across the capacitance, is equal to the excitation times quality factor. Excitation times quality factor. And your excitation is constant and it is known also. Means the circuit excitation I'm talking about, the value of the voltage you are applying, this is constant, will keep constant. You are required to keep it constant. So obviously as the quality factor will change, your voltage across the capacitance will change. So concept is that by measuring the voltage across the capacitance, we can measure this is called resonating capacitance. We can measure the quality factor of the coil. This coil, this is your coil. So in this setup, you can see that this is the basis. And in this setup, once you with all these discussions, I'm summarizing it, or rather concluding it. So in this case, as the resonance is achieved by whatever way, means by varying the frequency of the excitation, keeping capacitance constant, or keeping the excitation frequency constant by varying the capacitance. So once this is done, then the voltage across the capacitance will give you the value of the quality factor of the coil. You have to calibrate it. Obviously, you have to divide the EC by E, then you will get. That is always known. So this is how, and this is the setup. This is the setup of the Q meter. This is your oscillator circuit. This is your variable resistance, and then this is very important thing, that the oscillator circuit basically excites the small shunt resistance. This is called very small shunt resistance. There is a purpose for that. Means we can excite this whole circuit by directly by oscillator also, but instead of that, why it is done so, I'll discuss it. But it is applied across the small shunt resistance, and this small shunt resistance behaves like a voltage source of very small internal resistance. That is the shunt resistance, and this is your
हाँ ये
coil.
बात नहीं सही
जी
ये
बताइए.
बात तीन तो गिरा लागे तो बहुत
हाँ भाई, कोई कुछ बोल रहा है? You need any help? हाँ बताइए. Who is speaking? हाँ भाई, फरहान. फरहान,
यस
क्या कोई 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 चीज पूछना
सर,
है
वो
आपको?
गलती से फोन
अच्छा, चलिए म्यूट कर लीजिए आप अपने आप. म्यूट कर लें आप, फरहान आप. So in this case, so this is your the coil, means these are the test terminals, you can say. This is your resonating capacitor, and you can see that your meter circuit Q meter is basically applied connected across the voltmeter is connected across the capacitance, and whatever value of the voltage we'll get here, that will be divided by multiply Q by meter. Means here there is a meter. So this concept is that whatever factor we'll get, we'll multiply this reading by that to get the, and that factor obviously will be equal to 1 upon excitation. So this is how this is the setup of the Q meter. So by reading this meter, we can find out the, and multiplying it with the multiply by Q meter index, we'll get the actual value of the your, this is your test terminal, you can say. Whatever coil you want to, whose q factor you want to you are interested in finding out, it will be connected here. And then procedure is very simple. Again, I'm telling you, either we are, if we are having a constant value of resonating capacitor, then oscillator frequency is varied to achieve the resonance, because every time you will connect another coil, then um, you have to achieve the resonance with respect to that coil, and after achieving the resonance, then you should take the reading. So this resonance can be achieved two ways: having a variable oscillator, variable frequency oscillator, and fixed capacitor, or fixed frequency oscillator and variable capacitor. So by varying the capacitance or by varying the frequency, whatever may be the case, we are supposed to, for given coil or given coil. Few information is given here. The wide range oscillator with the frequency range from 50 kilohertz to 50 megahertz delivers a current to, and you can see that the value of RSH is very small, 0.02 ohm, and it is taken intentionally, because if I'm coming to that point, you try to understand. Um, in this case, if we are not using this shunt resistance, so obviously this oscillator circuit will have certain value of internal, I'm not only talking about the oscillator, but oscillator circuit is having internal value of the resistance, and that resistance obviously affect the Q factor of this test coil. So to get rid of that, the voltage is applied across oscillator voltage, excitation is applied across the shunt resistance, whose value is very small, as the typical value is mentioned over there in the next slide, that is 0.02 ohm. So this shunt resistance basically will behave like a voltage source of very small value of internal resistance, and that will basically, although this value will also affect your result, but it will be very small, and I'll try to show it also. So that's what it is written. The value of this shunt is very low, typically an order of 0.02 ohm. It induces almost no resistance into the oscillatory circuit, and it therefore represents a voltage source of magnitude E with a very small internal resistance. That's what I told you. Then how can we achieve the resonance? To make the measurement, unknown coil is connected to the test terminals, and circuit is tuned to a resonance either by setting the oscillator to given frequency and varying the internal resonating capacitor, or by presetting the capacitor to desired value and adjusting the frequency of the oscillator. The two ways are there. The Q reading on the output meter should be must be multiplied by the index setting of the multiply Q by meter to obtain the. Actually, this is the calibration factor. You can see, you know, EC upon E. So excitation voltage. So that index will be proportional to 1 upon E. So by multiplying that index value to the reading of the voltmeter that you connected across the resonating capacitor, that will give you the actual value of the Q value of the coil. So this is how experiment is done, and this is how it works. If anybody is having any question regarding these things, this circuit and other explanations on all explanation of the circuit that I gave you just now. So if you are having any question regarding that, I'm ready to explain. Okay. Now I'll try to show you how important is this internal resistance value. Here I took one example. Suppose your coil resistance, your whatever coil whose Q factor we are interested in finding out, if its resistance value is 10 ohm, and the insertion resistance, that your shunt resistance is 0.02 ohm, oscillator frequency is 1 megahertz, the tuning capacitance is set at 65 picofarad. So basically at 1 megahertz and 65 picofarad for a given coil, test coil, the resonance is, means your circuit is tuned to the resonance. So obviously the effective value, the true value of the coil, Q factor of the coil will be equal to 1 upon omega C R, मतलब XC upon R. R हमें coil का मालूम है, DC टेस्ट से हमने R मालूम कर लिया, और कैपेसिटेंस की वैल्यू हमें मालूम है जिस पे रेजोनेंस अचीव किया हमने, and we'll took the ratio of XC upon R, and so this is the correct value of the true value of the quality factor of the coil. Now I'm coming to the measured value. When we'll use the Q meter, so obviously this Q meter, the internal resistance, the RSH will appear in series with the resistance of the coil. So this will affect the accuracy of the, and you see this is very small value, and it will modify the actual value of the quality factor of the coil. Actual value is 244, true value is 244.8, but the measured value is 244.4 because of the insertion resistance, although this value is very small, and this is why we took care of it. If this value is higher, then obviously this error is more. So this, because of this small value of the insertion resistance, your error is coming out to be 0.16%. Is it fine to all of you? So this is one of the potential cause of error in Q meter, is your oscillator internal resistance, and to take care of that, this circuit is modified like this. That the whole excitation is basically dropped across the small value of shunt resistance, small resistance value, it is around 0.02 ohm, and then this works as a voltage source for whole circuit with the very small internal resistance. And even though with this small value of the inside your resistance, your error is coming. There is an error in the measurement. Although this error is also not very high, it is very small. But you can see that you can find out the if it would have been more value as far as the your oscillator internal resistance is concerned. So this is the justification why we have used this kind of arrangement. Now another potential cause of error that is not possible to compensate within the system, then we are required to calculate it. It is called distribution resistance, the distribution capacitance. So when we are connecting the test coil across the test terminals, these are the test terminals, then because these two terminals obviously will sit at the different potential, then there exists a distribution capacitance between these two terminals of the test coil, and obviously this distribution capacitance is going to affect your result. So it is not possible to compensate, because if you want to compensate it, then you have to keep these two terminals at the same potential, and practically it is not possible. So it is required to calculate the value of this capacitance and then you correct your result. Obviously your capacitance value will change and your Q factor will also change, because your effective capacitance will be. So the method which is used for measurement of distribution capacitance is although very simple. First of all, the frequency of the oscillator, the first time the tuning capacitance is set to the maximum value, your tuning capacitance is set to the maximum value, and the oscillator frequency is adjusted. Means we fix the frequency of the tuning capacitor to the maximum value, and the oscillator frequency is adjusted, is varied to achieve the resonance. The frequency of oscillator is F1 and the value of capacitance is C1 are noted. Then we have to note down the frequency of the oscillator at which your circuit is tuned to the resonance, and the maximum value of the capacitance, tuning capacitance. Now the oscillator frequency is fixed. At now oscillator frequency, we change from F1 to the twice of the F1. This time we obtain the resonance by varying the capacitance, by varying the value of the capacitance, and suppose this is C2. Means when we have doubled the frequency of the excitation, then the resonance achieved for at the another value of the capacitance, and this value of the capacitance C2. Now we are having four readings. One is your F1 and C1, other is the F2 and C2. Now F1 is equal to obviously 1 upon resonance condition. From resonance condition, this expression means resonance condition is your Xc is equal to Xc is equal to XL, series resonance condition. This is XL is equal to. So from this, and obviously this capacitance, distribution capacitance, although it is not real capacitance, physical capacitance, but it is a basically stray capacitance, you can say. So this will be the issue. It will affect the value of the tuning capacitance. So this will be your formula for the resonance frequency in first case, where the C1 and F1 is there, and in second case obviously it will be the F2 will be equal to 1 upon 2 pi L C2 plus CD, and your distribution capacitance will remain same, because we are not changing the coil, we are not changing anything, so it will remain same. And the F2 is equal to twice of F1, so twice of F1 is equal to F2, you see. So we equated them, twice of f1 is equal to f2, twice of f1 is equal to f2, and then we simplified and we are able to find, you can see with the help of we got our expression. With the help of this expression we can find out the distribution capacitance. And obviously, with once you are able to find out the distribution capacitance value, now with before finding out the um, means whatever value of the q factor, you will find out. I'll show how correction is done, and you can make the correction from the measured value, whatever measured value of I'll try to show you here. In this numerical problem, find the relation between the true and effective value of the Q of a coil when CD is distributed capacitance and C is the resonance capacitance. Following are the two measurements. जो two measurement हमको लेना है F1 C1 and F2 C2. You can see that F1 and F2 are F2 is twice of the F1. Calculate the distribution capacitance and the true value of the Q when the R is equal to 10 ohm for the both the measurement. Coil resistance is given. Now, first of all, it is asked that we are supposed to find a relation between true and effective value, measured value and true value of the. So you see, this is Q is equal to 1 omega L upon R or 1 upon omega C. The true value will be obviously 1 upon omega CR. The effective value will be, means measured value, will be 1 upon omega C plus CD into R. Now we'll take the ratio of this true value and the measured value. So your true value will be equal to the measured value into, so this is the formula. This is the formula you can use to correct your measured value, and this formula will give you the means effect of the distributed capacitance will be taken care of. And so obviously you should know the tuning capacitance value, that obviously you will know, and the distribution capacitance value. And distribution capacitance value is measured with the help of this method. So once you know the distribution capacitance value, then you can put it here in this formula. You can find out the true value of the, so this true value will be free from the effect of the distribution capacitance on the measurement. Now I'm coming to the the numerical problem. I'm coming to the formula through which we can measure the CD is equal to C1 minus 4C2 upon 3, and all these values are given here. So this way, so distribution capacitance, you can see it is 30 picofarad. Now once you are able to find out the distribution capacitance value, now this is the your effective value of the Q factor, and this is your true value, right? From this formula we are able to calculate, although the measured value is 16.578, but the true value is 17.693 as far as the Q factor is concerned. Obviously Q factor is a frequency dependent, so generally we speak about the frequency also. Similarly, in second case, means we are having two readings, one reading in second case it is 33.774 and the true value is 44.232. So this is the way we can take care of the effect of distribution capacitance on the value of the Q factor, measured value of the Q factor in a Q meter. All these discussion that we are doing, it is with reference to the Q meter. So if anybody is having any question, you can ask, please. Yes, please. So this topic I'm finishing here, and few more topics that I plan to take that that I will. So if you are having any question, you try to absorb it by the time I'll take your attendance. Then I'll start the fresh topic.